First thing first, we should know about thermosetting polymers. Thermosetting polymers are a class of plastic that once cured or hardened cannot be remelted or reshaped. Unlike thermoplastic, they undergo a chemical exchange during curing, forming a rigid and heat-resistant structure. These materials are extremely important in both industrial and commercial applications. From aerospace and automotive parts to electrical insulation and household items, thermosets are valued for their strength, durability, and resistance to heat and chemicals. In this video, we will explore two widely used thermosetting polymers, which is epoxy resin and phenolic resin. We'll highlight their properties, uses, and the latest advancements that are enhancing their performance in modern industries.
Now, I am going to explain about the synthesis of phenolic resins. Phenolic resins are formed by the condensation reaction of phenol and formaldehyde. If the formaldehyde into phenol ratio is less than 1 and an acid catalyst is used, the product is lophonac, which needs a curing agent to harden. With formaldehyde to phenol more or equal than 1 under basic condition, the product is resolved, which is self-curing upon heating. These reactions lead to a cross-linked structure that gives the resin strong and stable properties. Next, we go to structure, properties relationship. The hardly cross-linked structure of phenol resins provide excellent thermal resistance, mechanical strength, and chemical stability. However, they are brittle, which limits flexibility. Second, we go to recent improvement or the innovation of phenolic resin. Recent developments in phenolic resins focus on making them eco-friendlier and more efficient. Low emission formulations have reduced formaldehyde release, meeting stricter environmental regulations. Second, advances in fire retardance technology have improved their safety profile in construction and electronics. Third, modified phenol resins now exhibits better fire stability and higher toughness.
Next, we move to the application. It can be used by aerospace, either electronics. It used as matrix materials in fiber reinforced composites, carbon or glass fiber composites. High thermal resistance and flame retardancy make them suitable for aircraft interiors, heat shields and structural parts. Low smoke emission and self-extinguishing properties enhance safety. Next, we move to electronics. Employed as substrates for printed circuit boards, PCBs, in laminated sheets, phenolic resins have good electrical insulation properties, used in encapsulation and molding compounds due to thermal stability. And flame retardant grades are crucial for consumer electronics and telecommunication devices to meet safety standards. Next, for epoxy resin synthesis, epoxy resin is a thermosetting polymer formed by the reaction of epichlorohydrin C3H5ClO and bisphenol A C15H16O2 in the presence of a base, usually natrium hydroxide. Main types of epoxy resin. There are three types of epoxy resin, which is liquid epoxy resin and the characteristic low viscosity and easy to process. Second, solid epoxy resin, high molecular weight and used in powder coatings. And third, no black base epoxy. It enhances thermal and chemical resistance.
Now I'll be explaining the structure-property relationship in epoxy resins. How the chemical structure affects the material properties. First, the epoxide glue allows cross-linking to happen. This gives the resin high strength and strong chemical resistance. Second, aromatic rings like BPA increase the rigidity of the structure, resulting in a higher modulus and a higher glass transition temperature or TG. Third, the cross-link density is important. A higher density makes the resin harder and more brittle, while a lower density makes it more flexible. Fourth, aliphatic segments help improve flexibility and reduce the glass transition temperature. Fifth, the type of curing agent used controls the toughness, curing speed, and thermal resistance of the resin. And finally, when hydroxyl groups are formed, they enhance addition and increase moisture uptake. Now, let's look at the applications of epoxy resins, specifically in electronics. Conductive epoxy is commonly used in printed circuit boards or PCBs as adhesive and interconnects. It can replace solder, especially in lead-free electronics like in mobile phones or sensors. These epoxies are made conductive by adding silver or carbon fillers, which allow electricity to pass through. Next, we move on to high-performance epoxy applications. These are used in aerospace-grade composites, such as satellites and aircraft electronics. They offer high thermal stability and strong dielectric properties, which help protect circuits from heat and voltage damage. They are also perfect for semiconductor encapsulation, which means they protect microchips for moisture and corrosion.
In comparing phenolics and epoxy resins, each offers unique advantages for different industrial needs. Phenolic resins generally more brittle, less flexible, and less visually appealing, with limitations in impact resistance and environmental friendliness due to the formaldehyde emissions. On the other hand, Epoxy resin provide mechanical strength, versatility with a greater flexibility in formulations and application across the coating, composites, and electronics. Next, phenolic resins dominate in areas requiring high heat resistance and structural integrity under stress. Epoxy resin are preferred for their adaptability, strong bonding, and fine surface finish. The choice between the two depends largely on performance requirements, environmental conditions, processing need, and cost considerations. Phenolics and epoxy resins stand as the two of the most important classes of the thermosetting polymer, each with the properties and broad-ranging industrial application. While both materials are synthetic resin formed through a polymerization process, the chemical structures, curing behavior, performance characteristics, and usage differ significantly. Thereby, requirements in engineering, construction, electronics, aerospace, and many other fields.